At this point, we're ready to talk about the concept of chemical bonding. We'll first introduce a couple guidelines for bonding and then move into discussions of ionic and covalent bonding. So to start, we're going to look at some simple rules for bonding. One is that only valence electrons are used in bonding. So if we remember the definition of valence electrons, they are those electrons that are used for bonding. So we have to remember how to identify valence electrons. So we're going to go back to our electron configurations. Take, for example, magnesium. Magnesium is in group 2 on the periodic table and would have electron configuration of neon 3s2. So my valence electrons in my main group are my outer electrons. So the 3s electrons, there are 2 of them. These are my outer and valence electrons. So there are 2 valence electrons that magnesium can use in bonding. We can write a Lewis dot structure for magnesium representing its valence electrons as individual dots. We place these individual electrons around each side of my elemental symbol as if it were a box. So I place one here and one here. This would be equivalent to putting them on opposite sides. So it does not matter where you place those electrons, just as long as they are placed individually before pairing them. Another example we can look at is carbon. Carbon is in my p block of the periodic table and would have noble gas configuration of helium, 2s2, 2p2. So again, this is in my main group. The s and the p block are my main group elements, and my outer electrons with the highest n are my valence electrons. And keep in mind that my core electrons are my previous noble gas configuration within the main group. And the last one we'll look at here is selenium. So selenium is a bit farther south on the periodic table, still in my main group. So it will have electron configuration of argon, 4s2, 3d10, 4p4. So my valence electrons are my outer electrons with the highest n. So my 4s and my 4p subshells are going to be my valence electrons because they are my outer electrons. Now the 3d electrons and my argon electrons are my core. So this is something to note, that in this lower portion of the p block, my core electrons are my previous noble gas along with the d electrons. The filled d shell becomes part of my core. So I have 6 valence electrons for selenium. So I place them 1, 2, 3, 4, then pair 5 and 6. And I forgot to do carbon for you, so we'll go back 1, 2, 3, and 4 valence electrons. So you need to be able to draw these Lewis dot structures for individual atoms in the main group only. That's my s block and my p block. The transition metals are going to be exceptions to bonding patterns that we see here. The second guideline for bonding is what we're going to refer to as the octet rule. The octet rule is the idea that atoms will gain, lose, or share electrons to reach noble gas configuration. That is a complete outer shell of electrons. The octet rule has many exceptions, and we'll expand on those as we move through the bonding unit. But just to start, let's look at those transition metals I mentioned. Take cobalt, for example. Cobalt has noble gas configuration of argon, 4s2, 3d7. So in this case, my outer electrons are my highest n as usual. So I have 2 outer electrons, and those are also my valence electrons. But in this d block, I have to add to that count my d electrons. So valence electrons in the transition metals are equal to my outer plus my d electrons. So cobalt would have 9 valence electrons. And you do not need to be able to draw the Lewis dot structures for these. And as I said, these transition metals will be exceptions to many of the bonding patterns that we see, and we've already seen them be exceptions to periodic trends. So we're not going to pay a whole lot of attention to the transition metals. Thanks for watching.